Hi, welcome to, oh, pardon me. Welcome to Introducing OneFuzz. I'm Justin Campbell. I'm with the Microsoft Windows security team here with Mike Walker, the lead responsible for the leader of the group responsible for building OneFuzz. Today we're going to introduce OneFuzz itself, talk about how Windows is leveraging it to handle the security at the scale of Windows, and also concurrently be releasing it open source. So spoilers, we're going to kind of jump to the end of the presentation at the beginning and describe the vision that we had at the beginning of the project, which is that developers could introduce a change to their code base, be that Windows or anything else at Microsoft, wait for the build and nightly validation, come in the next morning to an automatically delivered message with all of the information necessary to reproduce and fix a bug that had been automatically detected, reproduced, deduplicated, and with all the technical details that we could possibly gather automatically. And the goal was to get a developer up and running in one day, onboarded into the Windows CI system, to keep this, to make it as simple as possible for developers to take advantage of the technology that we had built and broaden adoption as widely as possible. So dealing with security at the scale of Windows is a tough job. There are roughly 6 million source files, mostly C, C++, but a variety of languages. 1,100 PRs a day. That comes out to roughly 19 a minute. Thousands of developers all across the globe committing to Windows every day, and 440 official branches. And an official branch is one that receives a nightly build and nightly test validation and acts as an excellent choke point for security teams like mine to perform validation steps, including static analysis, dynamic analysis like fuzzing, and so on. And so the way we tend to think about finding vulnerabilities and software flaws in native code is part of this vulnerability discovery funnel. And at the top of the funnel, the most broadly applicable and cheapest to employ techniques like static analysis. And at the bottom are things like red team. And so when we think of static analysis, that's automated code analysis. Microsoft has world-class static analysis built into the compiler and in additional tool chains. And we try to do those things at PR time and as early in the developer loop as possible. And we're now experimenting with an IDE inner loop experience there as well. We then also like to think about scalable fuzzing. How do we have developers perform automatic dynamic testing of their code, roughly at the same time they would run their unit tests when things are expected to work. We perform automated attack surface analysis. So this is churn, where you have changed code on something that's already on the attack surface, as well as when you're adding new attack surface. And the best time for us to do that is around build and integration time. There are also other techniques, dynamic sanitizers, that we'll be talking a little bit about today when we do flight testing. And flight testing is a Microsoft term for when we deliver early copies to early adopters and enthusiasts as part of the Windows Insider program. And then there's pen testing, which is predominantly the activity that teams like mine do, which is validating the implementation matches the design and also looking for possible implementation flaws, be they architectural or code flaws. And then finally, all the way to the right are red team. And so that's a true black box, start from binaries, reverse engineer, find a flaw, write an exploit, and use that to help teams and stakeholders understand any actualized risk. And so the things we're going to be focusing on today are going to be scalable fuzzing and dynamic sanitizer technology that enables scalable fuzzing for developers. So let's also think about the scale of issues that come into Windows. So a CVE, if you're not familiar with it, is essentially just a unique identifier for vulnerabilities in published software. So flaws in any piece of software that were never shipped to customers won't receive a CVE. And so this chart is showing the number of issues reported either internally or externally in a shipped Windows product. And you can see over the years there's been an increasing amount of attention both internally with investment and externally from external researchers with strong incentives to find issues. And so 2020 is looking pretty good. If we naively annualize that, we're looking to be flat or a slight uptick from 2019. Roughly 80% of these issues are found with fuzzing. Of course, there is some bias in this data. As I mentioned, Microsoft already leverages world-class static analysis to find issues early in the development cycle. And so that tends to filter things out earlier in the pipeline. And so then they never make it to a delivered product and thus never receive a CVE. There's also external finders, of course, don't have source, don't have private symbols. And so they're limited in the tools and technologies that they can use to find vulnerabilities before they report them back to us. So Windows has a pretty generous bounty program, which pays external finders. And there are a variety of incentives in the security industry to be the ones to find issues and report back to Microsoft, and that leads to some recognition and PR as well. So all of those incentives really lead to a massive concentration of effort on finding vulnerabilities in these shipped products. And so if we think about the history of fuzzing, we can go all the way back to the 50s, and I'll give you just a moment to digest this anecdote here. But what it basically says is that even in the days of punch cards, the earliest developers had figured out that there was a real benefit to taking inputs for your program that were syntactically valid. They were well-formed punch cards, but semantically invalid. They were literally garbage. They were inputs that were never intended to be processed by the program that you're feeding them to as inputs. And so maybe they were the ones you used to program code. Maybe they were mistakes from earlier formats, etc. But ultimately, when introducing those inputs into their programs, they shook out undesirable behavior, and it was the earliest form of dynamic testing. They didn't call it fuzzing then, but they had effectively stumbled upon it. And then fast forward to 2016. So this is a picture from the Smithsonian where out of a machine that won a DARPA contest to automatically find flaws in software, reproduce them, and patch them. So 70 years has led to a lot of advancements, and it's still a rapidly shifting field. And so, we want to invite you to reconsider any assumptions you may already have about how expensive it is for developers to begin fuzzing, the costs of those, and capabilities of fuzzers. And one of the major advancements in modern fuzzing, and perhaps in the last 10 or 15 years even, is in coverage-guided fuzzing. And so let's start by considering this toy program that I have on the left here. And we have parse function with an array of bytes and a corresponding size. And we can assume that size is a trustworthy value for the valid length of buff. And then we have a couple simple check functions there. We verify that there are at least enough bytes for us to do some basic parsing, and then some early guard checks. The first byte must be X, the second must be Y, and so on. And then we can imagine after those initial checks, we do our actual work. And so perhaps we allocate some memory, we do some further parsing, and then in a refactor or a simple typo, we've introduced a double free. And a double free is an exceptionally powerful vulnerability when it does occur. It's very likely that when it does occur, an attacker will be able to leverage that for arbitrary code execution, where they're able to influence the state of the program and that input. So let's then think about how we fuzz this target. Fuzzing is fundamentally executing the program and monitoring for crashes or other spurious behavior. And the way we start fuzzing is with coverage-guided fuzzing at least, is by selecting an input from a corpus and mutating it. And corpus is just a term of art for a collection of input seeds. As I mentioned before, it's those syntactically valid, semantically invalid, or perhaps even semantically valid at the point where we're starting fuzzing. And so if this is an image parser, perhaps it's a well-formed image, or perhaps not. And then mutate it is just another term of art for performing perturbations on the input prior to introducing it to the program. And by that, we can mean randomizing certain values. We can smash in magic byte values that we know are likely to cause problems. We can invert the values of bits. We can transpose sections of the input. Really, the sky's the limit to in terms of the creativity of the fuzzer author as far as what can be done as part of mutations. And there's a huge body of work here in academia and in the security industry on what makes a more valuable mutation and what types of mutations are more effective on different types of parsers and programs. So then we need to introduce that input. So we trigger parsing by invoking the program in such a way that the input that we have mutated will reach our target function on the left. And so buff will then contain the value that we have mutated. And here's where the magic starts to happen, is we measure code covered. And with modern tools and techniques, there's a variety of ways we can do this, but we can, for the moment, assume that we have compiler-introduced instrumentation to determine which code was hit when a new input was generated. And that can then lead to a variety of valuable behaviors where if we consider passing in the word test as the value that buff points to, when it does that initial comparison against X, we can hint to the runtime that is measuring and executing and guiding this fuzzing that perhaps X is valuable to the, as worthwhile to consider in introducing somewhere in the input. And then such later might actually be, might be able to pass that check function. On new coverage, once we know we have a value that gets us past a check, we save that input back into the corpus, and it's now a candidate for further mutation. And then we do this hundreds of thousands of times per second. Because so much of the work that we're doing as fuzzing is probabilistic, we really need those large sample counts to get us the outcomes that we're looking for. And so the first piece of feedback that we always get when introducing this concept to developers is, well, that's great. This is a toy function. My program is infinitely complex. It has all of these edge cases that your thing won't handle. And here are a set of sample inputs from a blog written by Michael Zalewski, who is the primary author of AFL, a broadly adopted fuzzer. These are automatically generated JPEGs. And so as the contents of this blog outline, he started with a single null byte in his single input in his test corpus. And coverage-guided fuzzing in combination with AFL eventually led to automatically generating fully parsable and displayable JPEGs. So something as complex and convoluted as JPEG can be solved with this type of process. It's very likely that the vast majority of parsers are targetable by this technique as well. And so coverage-guided fuzzing will help. As I mentioned, it will help discover magic numbers and guard checks looking for immediate values, but it won't calculate hashes, it won't break crypto, and it doesn't understand. It isn't reasoning about the relationship between an immediate or where that goes in the input. Naive or relatively straightforward coverage-guided fuzzing instead relies on that probabilistic approach of saying perhaps this immediate is valuable, and perhaps we can wait for it to land in the correct position. And in reality, this actually gets us very solid results that we'll talk a little bit about later. So what is it like to actually harness a target for fuzzing with libfuzzer? So libfuzzer is a coverage-guided fuzzer written by Google and introduced as part of the LLVM project. And it's an incredibly valuable shift in paradigm where you can think of libfuzzer as a unit test framework with a fixed contract. And its contract looks exactly like that parse function that I showed earlier. There's an array of bytes with a corresponding size, and the corresponding size can be assumed to be trustworthy. And your job as a test author is to introduce that generated or mutated input into your program. And so here's a real world example where we're fuzzing the X509 parser that's used in Windows. And we're taking the data and we're specifying a number of configuration parameters, which in this case is saying, please interpret my data as an X509 certificate. And then we're introducing it into the target. And then on line 17 through 19 there, you can see we're doing some cleanup. So if this was successful enough to allocate resources, be sure to clean those up so that we can then continue and not exhaust memory or exhaust other resources. And so this is it. This is a 20-line test target that's actually in use in production today. And in terms of building and what it looks like to modify your build system, you can see what we've done here with unedited sources used with build.exe. We've enabled address sanitizer, and we've included the libfuzzer lib that is responsible for kind of implementing the driver and performing the callback that we've implemented here. And so this gets us a long way towards that 1 day of developer time goal to get started fuzzing. If we look at another case study, we actually also perform this technique on a variety of parsers in DHCP. And so DHCP obviously is a network protocol. And the Windows implementation is native code, and it's actually a variety of self-contained parsers. And so it's almost an ideal target. And with coverage-guided fuzzing, with no seed corpus, like no human-provided inputs, with 200,000 iterations per second, in roughly 30 seconds, we exhausted, or we reached 72% code coverage and roughly stabilized there. This work actually then resulted in 4 publicly documented vulnerabilities, and 2 of those were remote code execution. And so the proof is in the pudding, as we say. Like, actually then spending the less than a day necessary to harness this target, start it running, get this performance, and now there's a durable artifact that can be run every time unit tests are run, and performs automatic regression testing, and also prevents future vulnerabilities from ever reaching customers. So let's take a slightly broader lens and think about how we got to where we are with compiler inserted instrumentation and fuzzing. The way most security teams work today is we employ security analysts to target the production binaries. So the same binaries that ship to customers and run on customer systems every day. And our goal is to reach this target where developers can write their own unit test-like binaries that are born to fuzz. They have a single purpose of performing fuzzing. And perhaps they share code in common, but not necessarily the final artifact binaries. The problem comes in when we then consider all of the problems that a security analyst has to solve. They have to think about how they're going to gather coverage. If we don't have the source, we're not able to modify the source, we're not able to recompile the source. Perhaps we're doing things like dynamic binary instrumentation, using PinTool or DynamoRio. Maybe we're using a platform-specific debugger or the platform's debugging APIs to perform that instrumentation. Maybe we're using page heap or electric fence to catch out-of-bounds overwrites and reads, etc. And so there are all these 80% solutions that the security analyst is expected to be aware of, piece together, select the appropriate combination thereof, write glue or write new tools when existing tools don't exist. And this is unrealistic to expect developers to also become subject matter experts in the whole domain of security testing, in addition to whatever they're already a subject matter expert in. And so instead, we look to compiled-in tools. And so a variety of these are, again, tools pioneered by Google, and now some of them available as experimental features in the Microsoft C++ toolchain. And so for coverage, we look at things like sanitizer coverage. For boundary detection, we look at things like address sanitizer, and other things we completely avoid, like having to introduce I/O by making that a part of the contract. And really the goal here is to pivot from the hacker bolt-on paradigm to introducing developer tools. We need to reach developers where they're already working in tools they're already familiar with and in paradigms in which they're already familiar and operating. And through all of this, then, we can rely on the security analysts to provide fuzzing expertise. They can write new fuzzers, they can ensure that they reproduce correctly, they can assist with regressions and automatic regression testing, and introduce and manage the corpora responsible for making widely available parsers fuzzable. And so once we've got self-contained developer-created fuzzing binaries like this, we then need to think about how we fuzz them at scale. And for that, I'm going to hand it off to Mike Walker, who's going to walk you through more of OneFuzz and how we perform fuzzing at scale.
Excuse me. Thank you, Justin. My name is Mike Walker. I'm a senior director at Microsoft Research. Thanks to CPPCon for inviting us to be here today. Today's talk is about the open source OneFuzz framework that we're releasing today. And that is a framework that was developed through listening to teams that develop products around Microsoft, like Justin's team and others, to developers and fuzzing authors at FuzzCon, the fuzzing conference this year, to the customers of the Microsoft Risk Detection Service that we've operated for years, and both listening to security engineering and developers. And the consensus story that we came up with through all these conversations was that everybody wants fuzzing and everybody understands the reliability and security upside. But everyone also agrees that fuzzing as it stands and as it's been traditionally done is hard, expensive to use, and it's expensive in terms of engineering. engineering work that could be better spent developing new product features. So I want to dive deeper into the revolution that Justin was describing through an example. This is our simple image resizing application that we're going to use to talk about fuzz testing and the compiler testing revolution. And the job of this service is to resize images. Its control flow is very simple. It takes untrusted inputs from the network, and it recognizes them as JPEGs or PNGs. And then it has to demarshal those into an RPC state machine. So JPEGs and their associated metadata go one way, PNGs go the other. Inside that state machine is the work of converting JPEGs or PNGs into an intermediary image format, and then resizing, and then reserializing in the user's requested format and sending it back. Now, if I'm a security engineering team like Justin's, then there's a significant amount of work to do to be able to test this network service, because it is a network service. It is stateful. And that means that it has to be fast and performant for the authorized users that are going to use it in high volume every day. And it also needs to be resistant to black hat hackers who have vulnerability research capabilities. So that means that we have to be able to test it better than they can. And my first problem is that I have to develop a networked pseudo client that tracks every feature in this service. To get inputs into a network service that is a production binary, I need to be able to generate high volume, high speed inputs into this service and then orchestrate the correlation of the effect with the input. That's a significant amount of work. The next thing that I have to be able to do is advance my slides. Well, technical difficulties. Here we are. The second thing that I have to be able to do is instrument production binaries. So production binaries are designed for speed, not instrumentation. And that means that I have to bolt on coverage, often through a dynamic binary instrumentation framework like Dynamo Rio or Intel's PIN. And then I have to bolt on crash detection, either through parsing cores or using a debugger. And then I have to be able to differentiate real crashes and investigate real crashes and differentiate them from instrumentation-induced crashes. So the net result here is, in our example, security engineering has full-time care and feeding of this testing framework. They have to write probably two clients, one for the RPC state machine, one for the network service. They're going to be doing a lot of investigation of each crash. There's probably going to be per app enlightenment using the dynamic binary instrumentation framework. And reachability issues are going to overtest the recognizer and undertest the serialize and send step. So what we're looking at here is a set of homework, not just homework for the software under test, but homework for the testing apparatus. Security engineering teams are tasked with building high performance compute, root causing crashes, testing every single input for reproducibility, uniquing crashes and figuring out whether all these crashes fall under one bug or different bugs. And then there's the whole job of fuzzer selection, corpora updates, the rest. So let's take this legacy application and rebuild it again with the compiler fuzzing regimen that Justin was describing. We're going to take each component and we're going to harness it with the LLVM test one input function prototype. And for each component, we're going to have a unit test that is cooked into the build system. And this unit test is going to contain the trifecta: coverage, sanitizers, and fuzzing technology, all built in. And the goal here is automated targets that you can build once and compile forever and vanish into the build system, kind of reducing that homework lift. So the compiler support that we've already covered is half of the story, and the other half is cloud fuzzing. The job management to be able to do testing in bulk with this massive number of test cases that Justin mentioned, crash deduplication, being able to check and manage the massive number of crashes you may get, making sure they reproduce, making sure they're unique, handling the onboarding of fuzzers, and using telemetry to get notifications. So let's try this out on the command line. Take a look at what it looks like. We're going to start again with that simple test program that is checking the input for X, Y, and Z. But afterwards, we're going to use the next byte to select a different critically important memory corruption flaw. And this particular sample program on its fourth byte will select from one of 8 different harmful memory corruption capabilities. So if we fuzz this thoroughly, we should get at least 8 unique bugs. And fuzzing with modern coverage-guided fuzzers is useful just on the command line. That's what it takes to build one of these unit test binaries, cooks into the build system very easily. And that's how long it takes for a modern coverage-guided fuzzer to determine that XYZ is the correct input for this program, and it starts generating crashes. And it's completely feasible for a developer to test this type of binary on their local workstation, to harness one of these binaries into a while loop, start generating crashes, and start generating a series of faulting inputs. You can see the crash and then its hash generated on the command line. The first one generated was XYZ0. Now, as useful as this is, with real software, this needs to scale. This needs to be a large process with lots of compute behind it, and there's a lot of data orchestration behind the scenes. So to solve the problem of how to take these unit test binaries, attach them to multiple fuzzing technologies, get them into the cloud, and handle all the data flows and crash management, we developed OneFuzz. That's how far libfuzzer gets on a local workstation. We can use OneFuzz to send it to the cloud. So I want to talk today about the OneFuzz framework. It is open source and it is self-hosted. So MIT license, this is here for you to run in your enterprise and to build and remix and change. And it's also self-hosted. That means it runs in your subscription. So your jobs, there is no hosted fuzzing service here. All your jobs and your data live in your subscription. And deployment of this framework does not take an Azure expert. The README that's linked on this slide will allow you to, if you have access to the AZ CLI and access to Azure, start this up in an afternoon and have a fuzzing instance that can scale to a company as large as Microsoft. So I want to talk again about that listening phase of listening to security engineering teams and listening to developers, and talk about how the OneFuzz framework attempts to solve the very different requirements of these two different teams. So as we talk to security engineering teams around the company and around the world, what we found was that we would hear feature requests, but they weren't feature requests. They were complete blockers. Security engineering teams often had unique requirements where if they couldn't meet that requirement, they would abandon the entire fuzzing technology if they couldn't make the change. Those requirements went from Windows and other operating system dependent products that needed to be able to take daily builds of their operating system and fuzz on that daily build. So they needed complete custom operating system support that was cross-platform. We have this problem on Linux. We have this problem on Windows. There were many teams that needed their own custom crash analysis tasks, and they needed to be able to plug in their own crash analyzer because there was rich metadata associated with their program that needed custom analysis. We had many security engineering teams that said, we need to be able to onboard our own fuzzers. We have private fuzzers that live in our subscription or our enterprise. We need to be able to onboard them easily. And if we can't do that, we have to use our own fuzzing rig. So what we developed was a Python software development kit where it's not just that you can change things because it's open source. You can change things because everything in OneFuzz is used and composed through this SDK. So all of our fuzzers are onboarded through the OneFuzz SDK, and it's made up of a collection of simple primitives. So jobs are collections of tasks. Tasks perform a primitive within a fuzzing workflow, and every single task and every single job is remixable and pluggable. So you can add your own input generators, you can add your own coverage, and you can add your own analysis tasks. On the other side of the fence, what we heard from developers was, we need simple, reliable recipes that just work and plug into continuous integration. So OneFuzz has a Python CLI, or a CLI that's accessible as a downloadable PE, where you can send in very simple recipes, get powerful defaults, and fuzzing should just work. So let's talk about how that line is set up and navigated component by component. OneFuzz had to be a scalable architecture. We needed to be able to handle software projects with thousands of concurrent libfuzzer targets, thousands of cores, but it also had to work the same way if you were fuzzing on 1 or 2 VMs. So to do that, we used scalable primitives in Azure. And the end of the road here is that everything is structured data in a file in an Azure Storage Blob container. So seeds are files, crashing inputs are files, executables are files, crash reports are files, and all of them live in the same, by default, 7 storage containers that are set up on every job. Your setup storage container contains prereqs. Inputs contains both the inputs you provide, if you start out with a corpus of valid inputs or inputs you want to test, and those you generate through fuzzing. All your crashing inputs live in a container. Your crash reports, which are kicked off automatically, live in a container. And then the container that you will care about the most is the unique reports container, where new entries in that unique report container by default can kick off messaging to your continuous integration system. We also have those bugs that failed to reproduce and code coverage data. Continuous integration on compile fuzzing. So we talked a bit about how developers want reliable recipes that just work. This is the default command line for getting a fuzzing job launched in the cloud. And we're going to fuzz a component out of our sample image processing application. Start with a template, take the image resizer project, JPEG functionality, build number 1, and the Linux available pool. So virtual machines live in pools. They are hot spares. So the pool is a size that you specify and set up, and every task will pull from the available pool. That means that in that phase in between local fuzzing and continuous fuzzing, where you're kind of setting things up and working with the framework, you get this very low latency, observable, debuggable interaction with the OneFuzz framework. Build-aware artifact preservation means we keep inputs over the life of a feature. As you're doing continuous integration testing of the JPEG feature, all the inputs that were created by last fuzzing run are automatically ported to the next fuzzing run and combined with your newly compiled fuzz target. And beyond these defaults, there are powerful options. So I mentioned the need to be able to do custom operating systems. That comes from a pool that you can set up. And you can do everything from pulling public images out of Azure VM image list off the Azure CLI. Anything in the URM format works, to using automation to take your daily build of an operating system and create a custom bootable image of that operating system. Or if you're an operating system dependent product, or you're doing something exotic like fuzzing a hypervisor using nested virtualization, you can create and test your own custom operating system image and then do all of your fuzzing on it. For scaling, we wanted to make sure that the same command line that you use to do continuous fuzzing at very small scale could be turned into large scale fuzzing with just one flag. So scale is just a number in OneFuzz. If you want to fuzz with a few cores, tens of cores, hundreds of cores, all you have to do is change VM count. Talking to security engineering teams, fuzzer choice was a really important topic, and the ability to onboard fuzzers was a really important topic. So this is a screenshot from last week's FuzzBench. And you can clearly see that when testing SQLite 3, that you get breakout performance from AFL++. More edges discovered more quickly. So it's clear to me as a security engineer, perhaps, that if I'm going to test my software, I should use AFL++. Here's a screenshot from the same FuzzBench test from last week of libpng, where HongFuzz achieves breakout performance and more edge coverage. Security engineering teams love results like this. They love learning about which fuzzing technologies should be adapted to which software and tuning the fuzzing mix. We also, when we speak to developers, realize that developers just want high quality reproducible results. They want the best testing and analysis, and they're not as concerned about what's happening under the hood. And we felt that the solution to this was very recent in terms of academic investigation. The EN Fuzz paper, Ensemble Fuzzing, presented at Usenix last year, came up with the remarkable result that when you allow these fuzzers to share inputs throughout the entire job to work as a team, libfuzzer, AFL, fuzzers like Redomsa, maybe a private fuzzer that you use, or fuzzers that are domain specific to your target, when they're able to swap inputs, they can reach coverage and bugs that no individual fuzzer in the team can find on their own. So we decided that one fuzz would be Ensemble by default. And so when you onboard a fuzzer or use the default fuzzers in the one fuzz framework, they all swap inputs and work as a team, and you don't need to worry about it. As a developer, when you're using these templates, that just happens as a property of the framework. And we wanted security engineering teams to always be able to bring their own fuzzers. So we have first-class support for libfuzzer, AFL, Redomsa, but we also have an examples directory linked on the slide that shows how to onboard other fuzzers. Demato, which is very specific to the browser domain, HongFuzz, OSS Fuzz. These examples are there in the directory, not just to be able to allow you to onboard those fuzzers, but to work as a template for onboarding fuzzers that are unique to your project, even closed source fuzzers that you may keep only in your subscription or belong to you. So I want to do some security engineering, use the framework on the command line briefly, while also noting that you don't need to do this in order to use OneFuzz. But what I want to point out here is that everything is programmatically accessible in the framework, and all data is structured. Data is JSON. The JMES path query language in step 1 is how all querying of the framework happens. And the idea here is that it should be interactive, it should be scriptable, and it should be able to interact with your automation. So in step 1, I will search for a job containing the substring 8763, just enough of the UUID to be unique. I will pull the unique reports container, and I will pull one JSON structured crash report out of that container. Here's what it looks like on the command line. And we're going to start this command line session where we left off with a fuzz target we had just built on the developer workstation. And we're going to launch a cloud fuzzing job. So there is that one-line template again from the OneFuzz CLI. And this is what it takes to launch a cloud fuzzing job of any size. There are the 7 containers I mentioned, and it's off. Now, the minute you launch a fuzzing job, you want to know how is it doing. So I just launched OneFuzz status top. This is fuzz top. The development team behind OneFuzz loves this view. You can see everything in your entire fuzzing instance in real time. At the top is the status of your pool. It's busy and free node counts. Next are jobs. So the job we just launched that is following the TIFF functionality with 2 crashes and 9 inputs is accompanied by longer running jobs testing PNG and JPEG with more crashes based on when they were started. And then all the individual tasks that are being kicked off by those jobs is at the bottom. Now I'm going to dig straight into the job I just launched on the command line. I'm going to say, using just enough of the handle from that job, 3FC, just the substring, get me that container and list everything inside it. And I want the unique reports. So those are my unique crash reports. I have 2 unique crashes so far. And if I pull that JSON file, you'll see again that all data is structured, that everything is a file in a container, and the ability to pull this, and then we'll run it through JQ so we can take a look at it in its structured form, has sensible name fields that you can plug into your follow-on automation. Maybe route different types of sanitizer bugs to different parts or different notification pipelines. The entire call stack is there. The ASAN log, anything that your security engineering team wants to be able to fire as a introspection-driven event is programmatically accessible from this CLI. But we also understand that this is what security engineering teams need, but it is not what developers want. When we talk to developers, they want the fuzz testing process to vanish into their build system and to kick off automatically. So in the OneFuzz samples directory linked from this slide, you'll see example YAML files that show how to launch fuzzing jobs from an ADO pipeline, and how to launch fuzzing jobs from GitHub Actions. And we also have examples on how to do new unique crashes and have those create notifications in Microsoft Teams or as ADO work items. So I'm going to show an example from Microsoft Teams. And like Justin said, when you work at Microsoft now, you can get messaged over your chat application with a new, unique, reproducible, fuzzing-induced crash in pre-production code. And along with that notification comes a direct link to the crashing target, a direct link to the input file, and a direct link to the crash report with a complete call stack included. And it really changes the way that fuzzing is viewed when every single bug is reproducible. The screenshots here are from our dev branch. This is a GitHub issue automatically generated by the OneFuzz framework. Talks about, again, the same fields, crashing input in our example program. Down in the GitHub comments are all the reproducing cases. So multiple invocations of the same bug unique as additional reports. And then finally, this part of the GitHub issue has the same metadata as Teams. And I want to call out one line in particular, which is the repro line. So this is a pastable command that allows for live programmatic cross-platform debugging of any bug found by the framework. And when we launch this on the command line, so I'll copy it out of my build system and paste it into a OneFuzz enabled command line, a series of things happens. Whether it's Windows or Linux, we're going to pull a hot spare VM from the specified pool. We'll do the key exchange automatically. We'll set up an SSH session for you. And then on the target, the known faulting input, the target is deployed, a debugger is attached, and we'll halt on entry. And because you have the call stack, this is a time when you could set up breakpoints. And you can continue, and the program is going to parse with sanitizers enabled straight to the crash condition. And we're using the same sample program that we started off at the beginning of the presentation with. And in this particular case, you can see that this is libfuzzer discovering XYZ1, and it's even available at line 7 of the call stack. That's the faulting input. So continuous fuzzing should not be about doing continuous homework. It should be about spending a day setting up maybe a fuzzing instance and some targets for your program. And then after that, the fuzzing program should vanish into the build system. And it should be about notifications that are immediate and actionable, that are easy to understand and make your code more reliable, help make you a better programmer. I want to take this slide right before we move to questions, which I've been reading, but hoping that future slides would answer, but we'll get to them. To spend some time thanking the OneFuzz team who spent the last year building this framework and getting it ready for global open source release. Our partners on product teams who've worked with us, used the framework, driven its development, Justin at Windows, Jonathan Norman at Edge, Sphere, SDL, teams around Windows, the Visual Studio team, Jim Radigan, and the customers are our Microsoft Risk Detection Service, all of whose voices are represented in the result we're releasing today. We also need to thank Google, Costia, the LLVM community for pioneering this compiler fuzzing revolution. You'll see their ideas and tools represented throughout the open source fuzzing community and the attendees of CPPCon and CPPCon for having us. Again, we are open source and self-hosted And we're going to be using this continuously at Microsoft and pushing updates to GitHub. And we're releasing it globally because we hope that this is going to democratize and make fuzzing easier for enterprises who for whom that security engineering task has traditionally been too expensive. So we hope that you fuzz with us on Windows and Linux operating systems using composable fuzzing workflows that you can edit yourself, using built-in ensemble fuzzing by default, programmatic triage that's hookable and customizable and can use your own crash analysis, automated result deduplication, on-demand live debugging straight out of your messaging system, observable and debuggable with detailed telemetry through App Insights, which we don't have a slide on, but it's there, and that App Insights telemetry is something you can use to create coverage guided fuzzing programs and crash reporting through Microsoft Teams. So at this point, I believe Justin can rejoin me, and we can take some questions from the audience. So I'm gonna please bear with me as I attempt to repeat some questions. Yes, OneFuzz is open source on GitHub, and we are happy to work with developers. And we'll, by the way, be at the Microsoft booth for the rest of the con to talk about people, to talk with people who are interested in collaborating or contributing to the framework. Fuzzing can be used for testing non-IO functions, and there is a huge body of work using fuzzers to discuss discuss state machines, differential analysis of implementations, etc. Maybe following on to that, I know that there is, I believe the project is CryptFuzz, but there is a project that uses fuzzing to discover divergent implementation behaviors between cryptographic primitives that should always have the same outputs for the same inputs. That's maybe one example of that. To answer other questions, I'm going to need to move over to the screen and scroll back. So maybe Justin, who's had more time to prepare, can pull one out of the stack.
Yeah, let me go ahead and read a question for you here. Does throwing exceptions count as a crash for purposes of a crash monitoring?
Do you want to take that one?
Yeah, sure. So today in technologies like libfuzzer, structured exception handling will handle that correctly. I believe the public implementation of libfuzzer does have a gap where C++ exceptions are concerned. That's something that my team and the compiler team at Microsoft are working to close. OneFuzz, on the other hand, that's entirely configurable based on how you've implemented your fuzzing adapter. And so Mike mentioned that it's composable and you can bring your own fuzzer, and it's incredibly flexible in what behaviors you treat as something worth reporting and whether you treat that as a crash for purposes of alerts and reports. Second question here, does the framework work with any programming language? Is it a black box testing tool? Mike, you want to field that one?
We say that fuzzing is good for any target that contains native code. So it's C++, but those are just the primary languages where fuzzing is traditionally used. However, it's worth noting that even with binaries that have stronger guarantees of memory safety, anywhere there are potentially unsafe components at the end of a reachability path, fuzzing is an appropriate solution. So you see fuzzing in the Rust community as well.
Now I can read another one for you here. Can we integrate with other CI environments, for example, TeamCity?
We haven't tested it, but the spirit of OneFuzz is that everything should be pluggable and integration should be easy. So that OneFuzz samples directory and those YAML files there are recipes for how we've done it with ADO and GitHub. But this is open source and contributions are accepted. So our answer is try it, let us know. And we're really interested to know whether the SDK is adaptable enough to make that happen, or what SDK changes we need to make so that can happen.
Okay, and next question, can we extend your framework with C#?
Well, it's open source, so I don't think there's a reason you couldn't. I will say that OneFuzz, when we talk about the language choice of the framework itself, it is primarily Python, um, and there is also a Rust component, and we've used Rust exclusively for the execution agent that happens on the target virtual machine because of Rust's, well, first, amazing runtime properties, but also its ability to be able to emit dependency-free cross-platform binaries without a lot of platform-specific code. So it is already a multi-language framework, and I'm sure you could extend it in C#.
Yeah, and I'll add to that that if you wanted to write a fuzzer in C#, that's obviously supported today with no additional work. And Microsoft is actually working with the .NET and C# teams on using fuzzing to fuzz C# and the .NET runtime itself as well. Okay, I think that's our total backlog.
I believe we've covered the questions queue. But if you'd like to have a smaller discussion after the talk, please come join us at the Microsoft booth.